Hello, we're about to begin the next session. And I just wanted to remind you that all of these sessions will be uploaded to YouTube. I have just uploaded the previous session, and you can check this website at the bottom. You'll see in the website for this symposium that there is a blog, and in there I'm posting all of the links of the recorded YouTube channels. All right, so with that, let me begin the session.
Dear all, thank you for participating in the EU-Japan Symposium on Advanced Technologies for First Responders organized by the FASTER project. I'm Tassos Dimou from the Visual Computing Lab of CERT ITI, and I'm the Deputy Coordinator of the project. FASTER is a Horizon 2020 project working on technologies for first responders since May 2019, and it is finishing this April. The FASTER consortium includes 23 partners from 9 EU countries and Japan. Out of them, 8 are first responders, and we have another 4 linked third-party organizations that are contributing. Let me give you a glimpse of FASTER technologies before we move forward to the main presentations. FASTER aims to improve the operational capabilities and the safety of first responders by improving situational awareness, risk anticipation, communication capabilities, cooperation and interoperability, and improved ergonomics. These tools include common operational picture capabilities, indoors and outdoors, locally or globally, the use of unmanned vehicles for disaster scene exploration and intervention missions, mission management capabilities through wearable devices and social media analysis capabilities, wearables for haptic communication, biomonitoring, and K9 units, augmented reality technologies for situational awareness, information sharing, and intuitive unmanned vehicle control, and tools for enhanced, reliable, and trusted communications. The FASTER technologies are tested in 3 challenging scenarios, including collapsed buildings during an earthquake in Madrid, Spain, a flooded area in Piemonte, Italy, and a terrorism incident indoors in Kajaani, Finland. Thank you beforehand for your attention. Please contact us in social media or in the emails that you see here for further information. Thank you very much.
Okay, so let's start with mission management panel. So it's the first one, actually the second one on this menu on top. So when you click on mission management panel, it provides a list of all the missions that are on the map. So for example, let me just here you can also filter out the list by starting and date and ending date, and also max results. Here you can see all the list. This is the result of 10 missions. If we click, we can see some data here when the mission has started and when the mission has ended. When we click on location, it takes us to the exact spot where the mission is created. When you click on this icon on the map, it shows you some information about the mission. When you click on edit, you have the ability to edit that information for the specific mission. Now I'm going to show you how to create the mission. We have a tab, create a mission. Let's zoom out a bit. Let's create a mission title. Yes, mission. Okay, so for example, we can set lower bound for 1110 and upper bound for 1120. Here we have the option to select which kind of situation you would like. So for example, let's select Japan pilot, organization of the mission during test. Select the team. If you want, you can put notes. Then here we have a small map, and let's zoom out. Select the location where you want to create the mission. Let's create it here, for example. And here we have the polygon tool. When you click on it, then you have the option to create a set of points. 1, 2, 3, and the fourth point, if you would like, then you double click, left click, and then you have the option to submit the mission. When the mission is submitted, it shows you a notification that it has been created successfully. When you go to inspect mission, now we can, for example, let's refresh the page. And you can go to the, location of each and every mission. I don't know, I'm not sure why it isn't working now. But as you saw in the previous presentation, you can go to the location. Not sure why it's not working right now. But this is the mission that we just created. This is a test. No, okay, that's the mission that we just created, and it shows as a point on a map. Next tool is reports. Now we don't have any reports. I'm not sure why. Maybe the partner who is working with us turned off that option, but let me try it in incognito mode just to be 100% sure that it's not working. Okay, so it's probably a problem with the browser with cookies. So we also have a functionality called reports. Here, just like in mission management panel, you can see all the reports that were generated and sent to the COP system, which we are visualizing and showing on the map. For example, you have the possibility to go to details of the report. And when someone is submitting a report and sending it to the Common Operational Picture system, then they can send the report with pictures, as you can see, and with some additional data. And there's also possibility to send the report with videos, but we don't have any examples here of a video. Also, just like in mission management, you can go to the location and it's going to take you to the exact location of where the report was sent from. Here we have some additional reports. And when you click on details, okay, so next tool is persons. Now, this is just a simplified data of which we are visualizing. When a person is using a tool from our partner, the tool is called Chatbot. You can see the location where the message is sent from and where the person with Chatbot tool was at the point when the chatbot when the message was created. And here you can see also the location of the user who sent. Okay, just like in mission management reports, you can see that you can filter out all the information. Next is communication. It's a very similar one, but instead of just seeing a person, you can see the message that was used on the chatbot and that was sent to the COP system. You can also go to the location where the message is sent from. Here it is. And of course, when you click on the icon, you can see some details of the message. Next tool is a tool called social media analysis. Let's click on it. So here we have a lot of information and we have a new screen with different maps showing you different kinds of information. For example, on this list on the right, you can see all the tweets that are related to some event. For example, you have an event called earthquake. Someone tweets about an earthquake, and if our partners are generating that data, they're also sending the data to us, which we are visualizing. And you can see here also with the type of event, you can see when the of course Twitter message is sent, and you can see the location of the message. And you also have the possibility from the COP system to share a tweet. If you have, of course, the Twitter account, you can share each and every tweet from the list that is showing some event. Down here, you can filter out some information. For example, if you want to filter out information that is showing on the map and also showing on the list on the right by hazard type, then, for example, if you want to select the wildfire, you select the wildfire. And you also have the information type of, for example, affected people. You select that and you will click search. It will filter out the information on the map, resulting in all those points. It will filter out the information here on the right side on the list of the tweets. As you can see, we have only tweets that are related to wildfire and that are related to affected people. And here we have a hazard count, a chart showing wildfire and people affected here. Next to social media analysis tool, we also have a very similar tool closely related to social media analysis called events. Let's click on events. Here we have a list of events that is also generated by our technical partner, and that is sent to us, which we are visualizing, just like social media analysis. And here you can have on the right side the list of events. For example, of course, you have the option to go to the exact location of the event. On the list, you also have impact estimation. For example, this information shows you the infrastructures that are affected by the event. Currently, there are none. But as you can see, you have many infrastructures that could be affected by the event. Also, the population that is affected by a certain event. And just like on social media analysis tool, you can select the information which you want to filter out. For example, let's only search flood. And if we click search, it will filter out the information on the map. And it will filter out the information on the list, showing only events that are related to flood. And here, as you can see, the information is shown on the chart, mainly showing flood. Okay. Next tool is 2D mapping, which I'm not going to be able to show you today because in order to show it, we need to closely work with our partners because they're using drones to do a 2D mapping. But I think we already have an example on how a 2D mapping should look. Let's go here. Here you have an example of result of a drone taking pictures and generating that pictures into 2D map, which we are receiving and which we are visualizing here on the COP. It's, as you can see, very detailed a rooftop of a building. Next tool is points of interest. You have the ability either to receive from other tools, from technical partners, points of interest, or to create points of interest directly on the COP. For example, if you want to list all the points that are shown on the map, and you can do that, of course. Of course, you can go to the exact location of the point of interest. You can see some additional info here. You can, of course, delete the points of interest. And if you want to create a new one, then you can right click on the map. You can select the point type. Let's try with victim. When you click save, it creates that new point. And here it is. New points of interest. with additional information. Okay. We also have some details showing a local weather station. So the next tool is weather info. Let's zoom out. As you can see, there is some weather station on the map. When you click on the icon, it shows you few data. For example, humidity, wind speed, air pressure, etc. But if you click here, and location, of course, takes you to the exact location of the local weather station. And if you want to see more details, then you click on the details, and it shows you additional information coming from the weather station, and that is sent to us on the COP system. Okay, now I'm going to show you another tool that is available on the COP. If you want to create a situational awareness area, you can click on the polygon tool here. And just like when you create a mission, you use the left mouse click, for example, once, twice, 3 times, and the 4th time, when you double click on the left click, you have 2 options. Either create a mapping request of the 2D map that I just showed you a moment ago, and you can also create a 3D map request. We can also visualize 3D models, but I'm not going to be able to show that today for the same reasons as creating a 2D map by our own on the COP, because it has to be in close collaboration with the partner that is having a drone and that ability to create a mapping request. But let's define a new situation, area name. So you can select the severity of the situation. And hazard type, natural, for example. And you click save. Here, you can have all the list of all areas that were created. And if you click on the last one that we just created, and if you go to, I think I have to refresh the page again, cookies, and if you go to hazard, and if you click show areas, the button here on the map, it shows you the area that you created. And if you click on it, you can see the information that was put into that creation of the area. Okay. You also have the ability to filter out the information on the map. We have a tool called Entity Filter. And for example, if you want to see only reports on the map, you deselect the others and you click Submit. And as you can see, now you can see only reports. If there are many reports in a very close area on the map, just like here, when you zoom out, all those points are clustered into one number. Okay. Let's reset the filter. And now, just like before, we can see all the information. And just like clustering of reports, there's also clustering of each and every entity. So if there are many reports, persons, and missions on the same area, it is all clustered into one number, as you can see here. There's also possibility. I have some mocked data that I can use and that I can send to the COP. There's also possibility to show smart textiles coming from first responders that are from the tools that are attached to their uniforms, and that are sensors are used on the tool, and data is collected and sent to the COP, which we are visualizing. You're gonna see in a moment. Okay, now I just sent the new biometric data, and as you can see on the map, it is shown here. When you click on it, you can see some additional information. You can see heart rate, respiratory rate, temperature, and this is all GDPR compliant. We are only showing the partners that are having this tool are only sending us information in color code, and based on that color code, we are visualizing heart rate, respiratory rate, and temperature. And you can see subject info here on the left side. And that is about it. That's all the functionality that I'm able to show you today. Let me stop sharing the screen. Hello, Yasushi. Are you there?
Yes. So is it the end of your presentation?
Yes, yes.
Okay, let me stop.
Hello, my name is Angel Soriano from Robotnik Automation. We are a mobile robot manufacturer company, and inside the FASTERS project, we are responsible for providing the managed ground vehicles, the UGVs, and also integrating different sensors on these vehicles, and also for developing some high-level functionalities like the autonomous navigation system and the 3D map algorithm. First of all, why we want to use UGVs in an emergency situations. Here I wrote some examples. The preliminary access to the scenarios, I think, is one of the most important things to have an initial detection and identification of a dangerous situation, and at the same time avoiding any human risk. But of course, the UGVs can carry several sensors at once and can use them to perform a remote perception of the environment, while first responders are monitoring the operation from a safe place. The other question is that what are the requirements for using this technology in emergency situations? For sure, UGVs should be easy to manage, should be also intuitive, reliable, flexible, and probably one of the most requested things. Non-technical knowledge should be required to use them, right? And this is what we are trying to achieve during this FASTER project. Inside the FASTER architecture, the UGVs are located at the edge level, and all the information collected by the sensors are sent to the fog level through the secure communication layer. This data goes to different interfaces. The COP, that is the Common Global Interface for all the FASTER technologies, and the ground station server. This ground station server has been added to the architecture to offer a real-time data feedback from the UGVs, and at the same time to control and trigger some events or functionalities like starting the 3D mapping module or create some missions for the autonomous navigation and these kind of things. These are the two UGVs developed by Robotnik for FASTER project, the Summit XL and the RV-Car. Both platforms form part of our product portfolio right now. Not at the beginning of the project, but not yet, right now, yes. Both have been sensorized, taking into account the requirements from the first responders and also the requirements from the pilots of the project. Let's see more in details the features of the Summit XL. This UGV is smaller than the RV-Car, and it has a payload of 65 kilograms. It has a differential configuration with 4 traction wheels with 500 watts of power. And the Summit has been designed and built totally by Robotnik from the scratch. So it's like our own unique model, let's say. These are the sensors that have been integrated into the Summit XL, and a stereo camera that we use for creating the 3D map of the environment, a 3D LiDAR to scan the surroundings of the robot, a thermal camera to identify abrupt changes of temperature or detecting hot objects or animals, humans, whatever. RGB camera with a pan tilt mechanism that allows to move and focus the camera to any interesting direction. And finally, a GPS device to receive the global position of the robot and manage the autonomous navigation. For controlling the robot, the Summit XL, we use a PlayStation 4 pad. There is mainly 2 ways to control remotely the Summit. You can connect directly the PS4 pad to the robot via Bluetooth, and this allows a range of teleoperation around 10 meters, more or less. And the other option is to connect the PS4 to the ground station server, having a long range coverage. Do it that works with 4G network communication, so there is no limits of range for this communication. Let's see one video of Summit XL. This is the platform. As you can see, it has a thermal camera, 3D laser, RGB camera, a stereo camera, and also the GPS device. Here we are looking at the interface that it's in the ground server, station server, where we can send directly to the robot some coordinates in GPS format, and the robot can move autonomously, and at the same time it's providing the video feedback from the cameras to the interface while it's autonomous navigating through the environment. Of course, the cameras can be controlled remotely as the entire platform. And now we are defining some autonomous mission where the robot should reach some navigation points that we have defined in the interface. And of course, we also offer the television module inside the interface to control remotely the vehicle. We have different controls. One is for the entire platform to move the robot around, but we have also the remote control of the thermal camera to focus on any direction. We can control also the zoom that we can do in the camera. Yeah, and I guess this is more or less what we can do with the Summit. We can visualize also the thermal camera here. We have there 2D map of the environment. You can see the measures of the 3D LiDAR. And some information regarding the battery and the velocity that the robot it's moving. Let's check another video. This is from Madrid, the Madrid mini pilot that we did. In this case, we use the Summit XL to explore the area surroundings of the building, and we were able to identify one person that was in the middle of the ground with the thermal camera. There you can see the emergency team helping the person. Okay, and then I have another video about the pilot from the pilot of Kajaani in Finland, where the Summit was used to get into the building. As you can see, there were some kind of narrow corridor, and we use the Summit XL to get into building, checking at the same time the thermal camera image and the RGB camera image. Exactly. And also we were testing there the 3D map operation. In this case, it was done with the LiDAR, and we create a 3D model of the building where the first responders could test how was the situation before to get into physically into the building. I have another example of the 3D mapping operation. In this case, it was done outdoors in the street. We were teleoperating the robot. Here in the interface, you can see we are starting the 3D mapping module, and here you can see the robot moving. It's a little bit speed up. The video has been speed up just a little bit, and in the right side you can see how the robot is building the 3D map, how is creating this 3D map with the colors and with the textures of the environment. And then you will see the final results of the 3D map here. This is the other strategy that we are using. One is getting the data from the LiDAR sensor, and the other one is this one. It's doing the map from the images that we are collecting from the stereo camera. Okay, I think that's more or less all about the Summit XL. Let's move on to the RV car. In case of the RV car vehicle, we started to work from an electric vehicle that was already in the market. This vehicle is like a car that can be driven by a person. Of course, we made some hardware modifications in order to automate the direction, the brake, the acceleration of the vehicle, and we add some extra batteries to feed from one side the vehicle and from the other side the sensors and the control box that we are using to automate everything. It has an Ackermann configuration in this case, and can carry 2 people plus 200 more or less kilograms. So it's quite bigger than the Summit. These are the sensors that we have integrated. We have 3D front laser sensors for obstacle detection in front of the robot, and a stereo camera for creating the 3D map of the environment like in Summit XL. We have 3D LiDAR also for detecting the surroundings of the robot. A thermal camera that in this case has been mounted in a crane. We will see in detail in the next slide. And a powerful lights for working at night, and of course the GPS device for the global localization of the vehicle. As I was saying, the crane is this one. We built it from scratch. With this crane, the camera can reach 3 meters of altitude, and it has also a pan tilt structure where you can move the camera in any direction. For teleoperating this vehicle is different than this in the Summit XL. We have in this case a secure pad. This pad is connected to the vehicle by radio and has a maximum range of around 1 kilometer, more or less. The main difference is that this secure pad has an emergency button, so in case that something goes wrong or something is unsecure, you can just press the button and everything will stop, and the entire vehicle will be stopped. Let's check one video about the RV car, how we think that it can helps in emergency situations. You can see here how is the size. We think that probably would be able to reach the affected area driving the robot manually, as you are seeing. I will move a little bit. Okay. So let's say that we arrive to a secure control near to the affected area. One person can get out from the vehicle and the other one can keep driving to the to be closer to the affected area, like that. And then when it arrives, it gets out from the vehicle and use the crane to observe from above with the thermal camera what is happening around. If we can identify something with the camera or detecting some object that can be interesting for something. And then we can use the interface to send the robot again to the secure control point autonomously. Here we are at the same time while the robot is moving, we are seeing the camera object identification where we will see some object descriptions here when any object is identified, like any other cars or people or something like that. Here on top, on the right top square, we can see the trajectory that the robot will do autonomously, and on the bottom we can see the thermal camera streaming in real time. So the robot, when it's moving autonomously, the lights are blinking all the time, just to show that it's in autonomous mode. And as you can see, it's following the different points of the trajectory. Here you can see the objects that have been identified, like other cars, by the camera. And finally it reached the control point. So then another option is to transport supplies, people or tools again from the secure control point to the affected area, like right now. You can see one person is in the car, but the car is still moving autonomously, and it goes to the affected area, autonomously. So it's following the trajectory, and then finally it arrives to the affected area. From the perspective of the driver, to see how it feels, this is another example of an autonomous navigation. We have defined a square of defined by the 4 points, as you can see here. And yeah, we are inside the vehicle while it is moving autonomously. Okay, I think that it's more or less is clear. The idea behind these autonomous ground vehicles. I hope you enjoyed the presentation, and it was really nice to have this opportunity to describe our technology in this context. Thank you very much. Have a nice day.
Hi, my name is Marco Luna from DroneHopper. I will talk about the role of the UAVs, Unmanned Aerial Vehicle systems in the FASTER project. As an introduction, we can say that thanks to the technology development in recent years, the UAVs now are present in some safety and security agencies. They play an important role in the disaster management, as in search and rescue operations, firefighting, flood, surveillance, traffic control. For instance, the DJI company reports around 500 incidents attended by drones since 2013, as we can see in the map. This map shows where the UAVs have an important role to attend this type of catastrophes. Some advantages of this type of systems, we can mention the low-cost technology. Compared with similar options like helicopters, airplanes, or aerial aircraft in general, UAVs are a low-cost technology because they can perform similar tasks without have bigger aircrafts. The people's safety are another advantage. If we take into consideration that we need to access to a dangerous place for people, the UAVs can manage to navigate to these places without attempt to the people's security. The flexibility of these systems is another feature. For example, they can be used we can use smaller or bigger UAVs depending on the applications, and they can work with the same system interfaces or with the same ground control system. The versatility is another characteristic, as we have many applications for indoors and many applications for outdoors, so they can be used in these two types of environments. And the time is another advantage, because it takes a low time to perform a UAV mission. You don't need to mount a lot of things to have your UAV working. The current technical challenges of this type of systems are now determined by the payload capacity. For example, the autonomy, the time that they can fly, is determined first by the type of energy that they consume and as I say, the payload capacity. For example, electrical vehicles, as shown in the figure, can manage to fly around 20 and 30 minutes in the case of they are powered by batteries. In the case of helicopters, they have fuel, but the time that they can fly or they can stay in the air is determined by the capacity of the fuel tank that they have. Communications are also another challenge, because many researchers in the literature are dealing with the range of communications, and they are trying also to transmit the more quantity of data in a reliable way. Related to this, the security is another challenge, because we need to have a secure communications, but also a secure system response in emergency situations. For example, flight patterns when the UAV loses communications, when the UAV loses a GPS, or when the communication with the ground control station or the RC device is lost. All of these are challenges that people are dealing with them now. To introduce the use of UAVs in the FASTER projects, we will mention that we have two levels of communications, the fog level and the edge level. The fog level is the level that it's online in the cloud, and it has a center of command. Many requests of missions are made in the fog level, and they are executed in the edge level. Also, communications as UAV position, attitude, or video streaming are made from the edge level, where they capture the data, to the fog level through the FASTER server. The first task that is performed by the UAVs is the 2D 3D mapping developed by CERT and DroneHopper. Here, the area selection and the mapping requests are made in the fog level by the web page, and the missions can be done for single or multiple UAVs. So the user, the operator, select the mission or select the area that he wants to map, and these missions are sent to the edge level for the UAVs. Also, this software can calculate the time, the mission time that take to the UAVs to complete the mission. Once the UAV receives the mission, the waypoint generations are performed in the internal level, and the interfaces for launching and monitoring the missions are managed in the internal level by the UAV operator. This is because the UAV operator need to have a qualification to make this, and this cannot be done in the command or the center command in the COP. When the mission is finished, the photos are uploaded to the COP. Once the images are uploaded by the UAV to the fog level, these images that are geotagged are processed in the COP, I mean in the fog level. With image processing techniques, a map of the current situation is generated and the results are showed in the global server, I mean in the web page of the application. As we can see in the image, these results are in this time, not in real time, but the map is get for the current situation. Another mission performed by the UAVs in the FASTER project is the monitoring and surveillance SWAR mission. In this case, the operator selects an area to explore in a local interface, and this program generates automatic routes for available UAVs. Depending on the number of UAVs and the distance of the mission, this software generates the most optimized route to perform the mission in the minor time. And the operator can launch all the UAVs at the same time thanks to this interface. In addition, the UAV reports all the time their state to the COP, so the global operator can see how are managing the mission. Also, a video streaming interface is uploaded to internet in order to see different types of information, like RGB cameras information, thermal cameras, the weather conditions, online sensors, and the state of the mission as the interface shows. Another application developed in the FASTER project and in the use of UAVs is to extend communications. This is made with the UAV relay that was developed by the Enough company and Dronehopper. The objective of this application is to extend the communications in a disaster scenario. How it works? The UAVs have mounted a device that acts as a repeater to provide internet to multiple IoT platforms. In this context, the COP is sending to the drone which is the optimal position to hover in order to bring the best communication to the IoT platforms. These positions are received from the COP, and the local operator is monitoring all the time the aircraft state. When he receives a new position to stay, he can launch to this position through the interface that are shown in the slide. In this slide we can see that the interface shows the operator where is the next target point and which is the altitude. This is a security issue in order to have control all the time, to have the UAV controlled all the time. Finally, another type of mission is the aerial support. This type of mission is requested from the COP, and it can be streaming support or delivery support. Streaming support means that we need a drone to point the camera at this point, and delivery support means that some first responders need medical supplies or some supplies to this point. In this case, the ground operator receives the emissions from the COP and sends the UAV to the requested point. Based on the GPS coordinates that the drone receives from the COP, it navigates autonomously to the point to bring the support delivery, as we can see in the video presented in this slide. The first responder can request this support in the internet application. They can prepare in a few minutes the mission, and they send the support to the victims in this case. As internal feature works in the applications for first responders, we can mention that we want to enhance the UAV coordination and communications in order to have UAV support from different agencies like firefighters or policers, and to have a coordination between all of their UAVs. As we can see in the figure, it could be done with a server in the edge level, with the server in the fog level with a cloud computing center, and using also repeaters along different environments. Another line of work is the use of the swarm of UAVs in the firefighting. In this case, the swarm algorithms were tested with small UAVs. If we can enlarge the size of the UAVs and the payload capacity, we can use the same algorithms for the firefighting missions to have UAVs that can spray water in this type of fire scenarios. The other line of work that we have in mind related to the aerial support is to bring maritime support. This can be done by enhancing the communication systems to reach more distances. This maritime support it will be used to bring aerial delivery or streaming to maritime platforms like vessels or ships that could need some medical supplements or something like that in their operations. For your attention, I hope that you have enjoyed this short presentation.
So good morning or good afternoon, depending on when the meeting will be handled. My name is Claudio Rossi, and I am a program manager at Fondazione Links, which is a private not-for-profit research center located in Torino, Italy. I lead the program on AI for industry and security within the research domain AI, data, and space. In a FASTER project, we are the task leader of the two tasks that I'm going to present now. So welcome to this presentation. I'm very glad to have the opportunity to present the outputs of these two tasks of the project very briefly. The first task is about a mobile application for effective response management. We started by collecting end user requirements from civil protections and first responders, and they asked us to implement a usable solution to allow decision maker to better manage the deployed infield forces before, during, and after emergency situation. However, the end user did not want a standard mobile application due to usability, support, and maintenance reasons. For this, we decided to implement the functionalities within a chatbot that I will present later. I will demonstrate live the functionality of the chatbot. And so these functionalities are to monitor the position of the people, the health condition, the status, the activity of in-field responders. For the health condition, actually, we implemented a wearable application that I'm not going to present today. Then to instruct mission and follow their progresses, and to receive multimedia situational report from the field responders and send communication to the in-field people. So all these will be realized also thanks to the global COP, that is the central communication and front-end point. And so the decision maker sitting at controls room will be able to interact with the chatbot via the GCOP. So the GCOP has already been presented, so is not going to be presented now. But just to briefly mention that we have used Telegram, the Telegram app, so they've developed a Dockerized module for handling this. Then we have an authentication system and with the standard OAuth authentication. And then we have an API gateway to collect all this data, to store in a database, and then to share the data with the faster GCOP. So now I'm going to present directly the chatbot that normally is called FasterBot test. Today, unfortunately, we had a problem, a technical problem. So the bot, we redeployed the bot in a different name, but the functionality will be exactly the same. For this presentation, I will have to use it through the web interface, the Telegram web interface, although, of course, in reality, the first responder are supposed to use the mobile Telegram app. Once you are in Telegram, you will search for FasterBot test and you will find it. And so you will be shown a chat, a simple chat. Like this. Now, what I can do with this simple chat, I will have some buttons, these buttons that you see below. And so let's explore the functionality one by one. So set my status. We have agreed this status. So either I am offline, not working, or available to work, in case also I am a volunteer or an employee. I am moving towards a destination, or I am doing an activity. So I can select like this, that I'm moving, for example, and then the chatbot reminds me that my location is a little bit outdated. So I have to share my location. I will do this with the mobile app because through the web is not possible. So now we'll send my current location. Okay, so in this case, my location has been updated, and now also my status. Let's assume that now I'm doing certain activity related to a fire, and I'm using a fire extinguishing system. So in this case, I have updated my activity and my status, and also I specified the activity I am doing. In this deployment, we only inserted one activity, but you can assume that we can insert all the activity that the employees are supposed to do in a fire, in a flood, in an earthquake, depending on the hazard. We can have different specification on the activity. Then I can provide a situational report, or see the report that have been provided. In this case, I have just generated a report before this presentation. So if I see reports, the reports are just geolocated pictures with description. So description is fire in the mountain of Musinè, which is a mountain near the city of Torino. This is a real fire that happened a while ago. And so you can see the picture here. And then I inserted in this report also some measurements, some details. So the details can be related to different things. can be measurements related to the hazard or damages or other things. So in this case, I will not show you now the generation of a new report, but I will see if I have some mission. In case a mission is created from the GCOP, to me, I will receive a notification. Now a mission was already generated 35 minutes ago, and it is red because it's not taken in charge, and it says to me that I have to control the fire on Mount Musinè, and it gives me the link where I have to go. So in this case, is this the Mount Musinè? Is this mountain that you can see here, maybe? Okay, is this mount here? And then I can take the mission in charge. Okay, and now probably I can also update the mission status by creating a new report. So a new report of type fire. I will write fire under control, and I will attach an image to say that the fire is under control. Now I will not add other content. I will finalize. I will attach a position where the fire was controlled. In this case, I will do it from the mobile phone because from the web is not possible. I will try to pick up the location, the real location in Mount Musinè, but let me do it very quickly. Okay, I have done the positioning, and I finalize it. Send the report. Now it asks if it is related to a mission. It doesn't take the mission for some sorry for this bug. We will investigate this. Normally, if there is a mission that is here, I shall be able to link with the mission. Let me check again. The mission here is taking in charge. So it is on. It is ongoing, the mission. So normally I should be able to see this mission. Anyway, I can mark now the mission completed when I complete the mission, and this concludes the functionality. So at the end, I will be able to see the mission with the associated reports. Now, since we had this little problem, I go on and show other functionalities. So for example, if the GCOP creates some communication, I can see the communication here, and the communication in this case was reported a fire on Mount Musinè. Please follow the instruction of the local authority. We suggest to stay inside with the windows closed until you get a different instruction. So this is to communicate both with first responders or also with the citizens that could use this. Of course, citizens will not have mission, but could provide reports that I showed before. Okay, and this concludes the presentation of the chatbot. Of course, I have some settings here to change the language. Japanese is not supported yet, but we can add it without problem. And then this is the search interval is a temporal and spatial filter. So how much time and in which spatial dimension from my current location I want to fetch content. So in a radius of 5 kilometers, 20 kilometers, etc. And also in temporal filter. So in the last 3 days, 7 days, 30 days, so I will be able to see only recent data and not all the data. So these are very important to adjust the amount of data that I am allowed to see. So thanks to this tool, we can have data collection, massive data collection from the field, then mission management, as we have seen, and communication that are created by the GCOP, and also through this status and activity and position update, I will be able to see from the GCOP where the people are and what they are doing. Now, let's do the social media, which is another task. And for the social media, the objective is to gather data from Twitter, which is the only social media that provides API free to use, with certain limitations, of course. But and then we want to take this data and automatically classify and geolocate and detect event and also estimate their impact. I will skip about the technology here, but it's also a Dockerized solution, so it can be deployed in any virtual machine, and it has a data ingestion, then a part on the media processing on the AI algorithm to automatically analyze text, images, and other metadata, and then also a backend with an SQL database for handling the data and sharing the data with other components. In this case, again, the GCOP in the faster context. I'm skipping a bit the performances of the algorithm, and I go directly to the example. So the algorithm here are just to mention the three components. So there is a text processing and classification that analyze the text and try to find the topic and the name entity in the text. Then there is a module, models that are extracting the most important and meaningful images in case of an event, and then an event detection algorithm that try to detect event, and an impact estimation algorithm based on rules that try to quantify the impacts in terms of affected population and infrastructure. Let's try to see this in action, and unfortunately in a real case that happened in Japan. So we detected through the module yesterday at 3 that there was an earthquake in the Fukushima prefecture, and we estimated as an impact already 1 dead people and 81 injured. I know from news about some minutes ago that the count is now 4 and 94 more or less, so we are not very accurate in doing this, but we are close. But the impact on dead people was true, and also missing people is true, but we don't know how many, and we know that there are injured. And we know also that the residential power network and facility are affected, but we don't know, and also an airport here, but we don't know how many. Facility, it says 1, but facility is very generic. So here also there is an example, and with respect to the volume, you can see that there was a peak of tweet yesterday, and then now is going down. And with the respect to the tweets are these, so the magnitude is reported, and also other informations, the time when it happened, and here the images that have been extracted, and they are scored by relevance. They are ordered by the relevance. And you see that here there are divided in places and incidents. So incidents, it reports an earthquake or collapsed building, for example, here, and the places outdoor, etc. So just to give you an example about the images, we got this image for this event, this image, and this image. So and other images as well. So these are the first ones by relevance. Of course, this module has a global coverage. So if I disable this, I put all the events in, and I can see all earthquakes in the world in the last 2 days. But if I see also other hazard, I can see also floods, fires, etc. And so in this case, the event detection algorithm is now running on these three languages, English, Spanish, and Italy, but it can be extended to more languages if required. And so in this way, we can enable emergency managers and other users to have a global view or also a local view about the events and fetch relevant images and relevant content. Of course, this is only a dashboard, then all this information is also structured in the FASTER GCOP. I'm showing this as a dashboard just for convenience, but all this information are also available there. Of course, I may say that these are all estimations, so they require a human validation. So for example, in Japan, many events have been triggered, but it is only one. This is only one event, one earthquake, but it has been triggered in many locations because people are speaking about this all over Japan. And so also the impacts here are very high because it is summing up all the impacts of all these events, but in reality are the same events. Also, it happens that it detects events that are false, are not events, emergency events, but are other kind of events. And so these algorithms are not perfect and require a human validation to have a curated list of events with the curated list of impact and images, and this could enable also to do a reanalysis of event of this historical database of events, and this is the main purpose of this module. This concludes my presentation. Sorry if I was maybe too long. So I thank you for your attention, and I hope that you will be interested in these solutions. If so, don't hesitate to get in touch with us and with me in particular. Thank you very much.
Hello, everybody. My name is Dimitris Koyas. I'm a member of the team from the University of West Attica, working for the FASTER project. I'm very glad to be here with you, even though here it means remotely. I hope next time I will be able to join you. Now, I will be talking to you about wearables in the FASTER project. And in fact, my presentation will consist of 3 tools: the animal wearable tool, the smart textiles framework, and the movement recognition for first responders, or MORS. So I will jump in, starting with the first tool, the animal wearable. Well, an animal wearable is a wearable for animals, of course, a novel wearable device, and the main scope of it is to be able to further enhance the assistance that's offered by trained K9 units in FASTER project. According to the description of action, the tool has been engineered and designed in order to provide real-time status recognition from the animal. And also the tool will be able to translate the animal's behavior into predefined messages. And those messages could be played back to the person in need. Now, in addition to what has been described in the description of action, and after discussing with the first responders in FASTER project, there are 3 more requirements that have been added to what has been already described. These requirements regard the shape of the tool, the dimensions of the solution, and of course the fact that what would be provided should increase the safety, should have highlight the safety of the animal. Now, in general, the tool is able to geolocate the animal, and also it has 2 more features. It can detect whether the animal is barking, and also it can also detect if the animal is standing or searching or is sitting down. Now, we do need this the combination of this information in order to be able to provide meaningful results about the activities of the animal. In fact, given the fact that it is a 3-year project, what we have been trying to achieve in FASTER is the fact that we needed the animal to perform a combination of movements and barks, such combination which already exists in the animal's training, in order to understand and point out in a message when the animal locates a victim. And in fact, this combination of movements includes the fact that the dog should sit down and bark. These 2 features, the bark detection and the activity recognition features, are the result of AI algorithms running on the wearable. And when these two features translate to a dog sitting down and barking, a message is displayed on, is being propagated inside the FASTER architecture, giving note to the fact that the animal has reached a victim. And given the fact that the geolocation is available, the location of this victim can also be shared within FASTER project. Now, the results are coming from the processes running on the wearable, and can be seen, can be depicted either in the command of operation, in the platform that is used for command of operation for FASTER, GCOP, or alternatively, these results can also be seen by a smartphone application that could be installed to the smartphone of the dog's handler. Therefore, there are 2 sources, there are 2 targets where this information can be seen in FASTER. Now, this is some pictures of regarding the design of the wearable. You can see, first of all, there was a collar, but after discussing with the first responders, we switched to a harness design. At first, the electronics were placed in the front of the animal, but following tests and also academic research, since we need the AI algorithms to run on the wearable, we have been able to start to see that there are studies that showcase the fact that better results come when the electronics are placed on the back of the animal, and therefore we changed once more the design of the wearable in order to have the electronics on the back. The wearable is modular. It has Velcros in every pieces of the tool in order to be able to separate it and use it with any combination needed for the task at hand. And therefore, it is flexible enough both to fit on the animal and, of course, to be used as it suits best for its action. Now, for the communication coming from the wearable, there are two communication paths. The first path, the primary path, is by using a Wi-Fi. If there is a Wi-Fi present in the area, then the wearable can communicate directly to the FASTER cloud and forward any information needed there. In case there is no Wi-Fi present, then there is a backup communication path that includes the use of an extra tool. We call it the base station. The base station is a device that is able to communicate with the wearable using RF communication. And also there is a hotspot on the base station that allows it to forward the data that are received through the RF communication path between the wearable and the base station. The base station is able, using 3G or 4G, is able to forward the data inside the FASTER cloud architecture. So there are two communication paths. This is the base station. Here is a solution with a pocket Wi-Fi that creates the connection for the communication of the data to the FASTER cloud. And this is the base station as a device solo. Now, the reason for having the base station is, of course, to increase the covering area. We do not need the Wi-Fi to be present. We can have the base station, and using RF communication, the animal can further advance into the area while still remaining in range, and the base station is able to collect and forward the data to the FASTER cloud architecture. Now, as I told you before, the first device that is able to display the messages coming from the wearable, the results coming from the AI algorithms processing on the wearable, are either the COP, the common picture of operation, or there is also the possibility to use a specially designed and developed smartphone application that is available to the first responder, and which is able to locate the animal, showing the animal on a map. And of course, the results of the processing from the AI algorithms regarding bug detection and activity recognition are also being displayed on the smartphone. And there is a message coming up, pop-up message, indicating when the needed combination of the dog sitting and barking is applied. Now, I will move to the next tool. This is the Smart Textiles Framework, or STF in short. Well, Smart Textiles Framework is a prototype solution, and it includes three parts. There is the First part is the module that we use for the biometrics measurements coming from the first responder. There is also an environmental module that collects data from the environment. And a third part is a software application that can be installed in the smartphone of the first responder, and which allows for the collection, processing, and display of the data. As an add-on feature, the smartphone application will also be able to forward propagate messages regarding the status of each of the measurement for each of the sensors. So the Smart Exiles framework tool can monitor biometrics on the first responder and environmental data around the first responder. These informations are combined and processed on the smartphone, a specially designed smartphone application, in order to generate messages regarding those measurements that could lead to a local situation awareness. These messages, these alerts or messages, are being displayed on the COP, on the command of operation, general command of operation. And the way that these messages are being propagated is fully compliant with the GDPR regulation for Europe. And therefore, there are no actual measurements that are being propagated, but instead, we use a color code in order to identify the severity of each of the measurements. Okay, so for example, there could be a breath rate which is a little bit higher than what is expected, and this could be displayed using the yellow color on the message. I have more photos later on. So let me introduce you to the two sub-modules that we use for the Smart Exiles framework. This is the biometrics module. This is the biometrics belt that is been monitoring the heart rate, acceleration, the breath rate, and the estimated core temperature of the first responder. This belt can be placed in this T-shirt that we have produced. It has a separate hole here for the belt, and this is used to make someone it will be easier for someone to wear the shirt instead of having to place the belt on himself or herself. So, and this is the environmental module, which consists of this device. This device has sensors that are able to measure temperature, humidity, and carbon monoxide levels in the area. And it can be placed inside this small pocket, and all these tools can be worn on the outside of the shoulder, outside of the uniform, in order to collect the environmental data. Here are more photos of the sub-module. And here is how the smartphone application looks. Here is the tab for the biometrics, and here is the tab for the environmental data. You can also see the colors showing here, which are mapped to a severity level for each measurement. Here is the degrees, the core temperature measurement, and it is okay, so it is green. We need this color here because when we will propagate the messages, this is how the Smart Exiles framework information is depicted in the GCOP. You can see here that there is the sensor, the name of the sensor, and also the color of the data to be compliant with the GDPR regulation. Okay, so finally, the last tool that I will be talking about is called MORS, for movement recognition for first responders. MORS is a mobile application for smartwatches and smartphones that it can be used to run AI algorithms on the smartwatch to identify pre-defined gestures, and that can be performed when oral communication is not a solution. Now, what this tool can do is can recognize these predefined gestures, 5 gestures for faster. I will be showing you more in a bit. And when these gestures are being recognized, alerts are generated and propagated. These alerts are propagated in the faster cloud architecture for further processing and notification, but can also be propagated locally to any first responders having a smartwatch with Morse. Now, these are the 5 gestures that have been selected for Morse for faster. I should point out that there is not only visual notification of the gesture that has been recognized, but there is also vibrations and oral communication for each received gesture. Here is the number of times that are needed for each of the predefined gestures. We have fire indication, recommend stop, recommend evacuation, emergency contained, and distress. This mapping of the vibration to gestures can be modified by the user of the Morse application. Here is a default mapping for each gesture. Now, here's a look of the smartphone application. You can see here the notification about the gesture. Here are some settings to control and settings. And here is the login screen for each user. Now, in general, these are a summary of the work that has been done regarding wearables for faster. I would like to thank you all for your attention, and I am open to any questions or discussions that you want to have. Please do share an email with me, and I will be very glad to be in touch with you. Thank you very much.
Hi, my name is Guillaume Engles from CS Group, and I'm going to present you the augmented reality tools developed into the FASTER project. I will start by giving you some context about augmented reality and the reasoning behind these tools. I will follow with a short description of the hardware we are using. Then I will present the augmented reality tools for situational awareness and collaboration developed by CS Group. And finally, I will finish with the tools developed by CERT team, the UXV gesture control and extended vision. In the FASTER project, we are developing tools for first responder. And in their daily task, they require full attention and the usage of both hands. So what the augmented reality can offer to support the first responder? First, visualize information in context with the real environment. So they don't have to look at a specific device screen. Information is displayed in front of them. Second, the displayed information is clearly visible even if the environmental conditions are degraded. Third, it can support them during complex operation by giving them a direct access to information and enhancing their knowledge of the situation. And finally, the augmented reality offers new perspectives for optimized cognitive load and information sharing. They have access to on-demand information and annotation. Now, let's move on to the work done into the FASTER project. The goal was to get the best out of the latest augmented reality technologies, to provide mainly relevant and targeted features, not an all-in-one tool. And a tool simple enough to avoid increasing their mental load. And this task, taking into account the technical limitation of the current AR devices. We rely on the hardware, but they are not ready for operational use. And it's challenging for an AR device to deal with new area or rooms with unknown or changing conditions. So now, let's present you the hardware we are using. First, the HoloLens 2, which is a see-through augmented reality device and also mixed reality device. What does it mean? It means that you can see around you when you wear it. In addition, this device comes with various sensors, allowing not only to blend holograms with the user world, but also to map the device surrounding to remember where the content is placed and to track the position of the helmet in its local environment. The second tool, it's the UAV DJI Mavic 2 Enterprise Dual, used to test the gesture control. We make it move with our hands and to provide the extended vision in AR with the HoloLens to see what the drone camera is capturing. Now, let's start with the AR tools for situational awareness and collaboration. These tools have been developed to provide the FR with real-time visual information about the situation and to provide them with capabilities to easily add information from the field. But what the AR can do for them? And why using AR? First, because it's hands-free, which is a big advantage compared to mobile phone. Secondly, it's possible to adapt the information display in AR to each user. But more important, to display geolocalized information linked to the current position of the user. This avoids an overload of information or accessing knowledge not directly related to the first responder task. Finally, we can provide means to facilitate the sharing of real-time information coming from the field and at a specific geoposition. The user doesn't need to describe where he is. The coordinates are transmitted. Now, let's see some implementation details. During the project, we developed iterative versions of mixed reality application, improving the proposed interaction and the visual metaphor to propose the best ones suitable for first responder, with menu in the hand, for instance, or holographic buttons. We also used the HoloLens 2 capacity to track the helmet position into its local environment and map the FR position to GPS coordinates, which provides a common reference for the geolocalized information sent and received by the FR. Now, let's move on to the features themselves. First, the AR minimap, which displays a map of the area. The FR can request it whenever he wants. This map shows the FR position with an arrow, giving at the same time its heading direction. We also display on the map the other team's member, point of interest, such as identified hazard, exits, or useful equipment. When available, we are also able to add an indoor layout, facilitating the first responder progression indoor. The first responder position and orientation is also shared with the COP. And thanks to a QR code placed into the scene, we initially calibrate the geolocalized system, and we are able to indicate the first responder, of course, position, geoposition, and current flow into the building. Now, regarding the point of interest, the COP and our user can create predefined type of annotation. From the COP, it is done by simply clicking on the map at the position where you want to add the point of interest. You also add some details, and that's it. This buoy will be visible in the field when the first responder will be next to it and looking toward the direction of this point of interest. From the first responder side in the field, adding a buoy is also very simple. You just use a voice command, like say add victim, add a risk, or select one from a menu you have in the hand. And that's it. The system automatically creates and shares the new buoy with the user current position. The other features we have into this application are the notification, visual notification linked to a mission or an immediate danger. Finally, we have added also a capability to send a distress signal and another one to take picture with the HoloLens 2 camera and share it as a report to the COP. Now, let's finish this part with a short video showing what the FR can see in augmented reality and on the COP. So first, you have the startup and the calibration. So when the application starts, of course, it will connect to a specific server, and then the first responder scan a QR code to calibrate its current position. What happened on the COP is that the first responder position is now visible. The first responder position is also visible on the AR minimap. So he simply requested with a voice command saying OK map. And when the user moves, his position is also evolving on the map. And so when you move around and you need to know your new position, you just have to call the minimap. On the COP, you can see also the first responder moving around. Regarding the annotation, the buoy. So the first responder can create one from the field with a voice command. Here, say add victim. When it has been added, you can see it in the environment, but also on the minimap. Now you have another sample with a risk. And both annotations are visible on the map. What you can see on the COP is new POI popping out. Here the victim and then the adult. In the top right corner, you have the list of POI created either from the field or from the copy itself. Here is how you create a point of interest. You select the type, enter some additional information, and save. You can see the new POI on the map. And from the first responder on the field, you can see it into the environment. Now let's see the annotation and not the annotation, but the notification, the mission here. So you create a mission from the COP with a description. You select the recipient, here the AR user, and you submit it. On the AR side, the user will see a notification inside the helmet. Rescue victim. Now he can either accept it or reject it. Once it has been accepted, you need then to say that it's completed. So you can update the status. On the COP, the operator is notified when the user accepts it, is taken in charge, and when it's completed. And that's it for the AR tools for situational awareness and collaboration. Now, let's move on to the tools developed by CERT team, the UXV gesture control and extended vision. Starting from the UXV gesture control. This tool was developed in order to be able to navigate drone using the hand gestures instead of the default controller. But why to do that? We believe that using gesture has some significant advantages. First, using gesture can be more intuitive for inexperienced users who have never navigated a UAV. It needs some time to learn using a controller, while when you use gestures, the user gets familiar more quickly. Secondly, by using gestures, there's no need to hold a dedicated controller, avoiding to carry unnecessary equipment, which is very important for first responder. Navigation can be performed also using only one hand. The other hand can be used to perform other tasks. Also, some specific controls can be performed faster with our system compared to using a controller. But let's first describe some key points of the approach we used in order to implement the gesture vocabulary. Gesture control should be an easy-to-learn interface. This can be achieved by using a metaphor. In our case, the metaphor chosen is that the drone corresponds to the user hands, and hands mimic and follow its motion. This way, for example, raising the hand higher will correspond to a drone ascending command. You can see the whole set of gesture vocabulary in the picture, like tilting to the left or to the right. Now, regarding the implementation details. The gesture application was implemented for the HoloLens 2, the AR device mentioned previously. Initially, the HoloLens was planned to be used mainly for extended vision. But because it's also robust hand tracking capability, we decided to use it for gesture control tool and combine the two tools, so gesture control and extended vision, into one application. After performing pre-development user studies, we concluded that user preferred using palm gesture with the whole hand instead of finger gestures. To facilitate the navigation task, visual feedback cues are also displayed in AR. The hand joints are visualized as cube, so the user can check if his hand is tracked correctly by an AR device. It's what you can see on the left picture here. You should note that in the picture, there is a slight transform error. The cube are not directly linked to the hand joint. But this is an artifact of the camera capturing the photos. In the actual app, the cubes are displayed exactly on top of the user hand. Another visual cue is the navigation feedback panel placed at the top of the AR display. This panel is visible in the right picture. In the navigation feedback panel, the passive UXV navigation commands, such as pitch, roll, throttle, are mentioned in real time, alongside with useful information, such as drone altitude, heading direction, ground distance between the drone and the user. Now, let's see some features about this tool. During the various pilots that took place during FASTER project, user had the chance to suggest changes and request additional features. They were then implemented and integrated into the application. About the camera gesture control, the default user hand used for navigation control is the right hand, although this can be modified for the left hand. The other user hand can be used for controlling the view direction of the drone camera. This feature is controlling the camera gimbal, which is able to perform a movement, rotation up and down, left to right. This gesture vocabulary, the gesture vocabulary used for camera control is similar to the vocabulary used for drone navigation. Then we have the periscope mode. It's an additional form of gesture control, which does not involve the user of hands, but it is based on the user head direction. When periscope mode is enabled, the drone viewing direction follows the user head direction in real time. For example, when the user rotates his head to look 90 degrees east, the drone rotates the exact same direction. Periscope is an auxiliary feature, allowing for quick and intuitive inspection of the surrounding environment. Finally, we have also voice commands that are used to perform high-level commands, such as resetting the camera direction. Now, let's move to the last tool, the extended vision. UXVs can be used for exploring dangerous or impassable areas safely from a distant point of view. And if they are coupled with see-through display, they can simulate X-ray vision to provide a natural view into an otherwise occluded environment. First responders have identified the added value of this tool, and they have defined specific requirements for making the tool more useful. More specifically, FRs want to have an easy-to-use technology and to be able to easily understand the drone position and viewpoint in relation to the operator's position, enabling them eventually to see the activities in the video in their proper location, offloading the cognitive work which is normally required to mentally register those views. The live video feed from the drone camera is projected on a canvas inside the augmented environment. The user can simultaneously be aware of his surrounding in the real environment, while also viewing the drone's video feed in his field of view. With minimal head movement and loss of focus, the user can perceive the surrounding environment from two different viewpoints. An example can be seen in the picture. The user located behind the building wall, while the drone is flying in front of the building. The user can see the AR in the AR application, the approximate location of the drone, represented by a red virtual drone, and the video feed of the drone's camera. Now, here you have some worth noting feature of this tool, the video registration. Upon request, the video feed from UAV camera is displayed in real time in the AR app. The user can choose between seeing the video in a stable position in the middle of his field of view. It's what you can see on the right hand picture, or he can choose to see the video in a moving panel that follows the position of the virtual drone and the direction of the drone camera. It's what you can see on the left picture. The second mode is called egocentric view. This mode is used to facilitate the visual perception of the drone viewing direction. So finally, two more features are available. First, the user can choose between different video modes provided by the UAV sensors: RGB, infrared, or hybrid videos. It's what you can see on the left and on the middle. The other features is the drone tracking. So this drone tracking feature has been implemented with a virtual drone in bright red color to be easily spotted. This drone follows a real drone and is placed on top of it in the user field of view. This is very useful for the user to quickly locate the real UAV that can be quite far from him and not easily spotted. Now, let's see a video showing you all the features in action.
In this video, we present the augmented first responder application and the currently available features. When launching the application, the automatic network configuration process starts. The configuring connectivity message indicates that the automatic network configuration is in progress. When network configuration is over, a new notification message appears. At this stage, we see the user executing the drone tracking calibration process. He grabs the virtual drone with an air tap gesture and places it on top of the real drone. Then the real drone is moved a bit further, and the user again grabs the virtual drone and places it approximately on top of the new position of the real drone. The drone tracking calibration is now ready. Now, the user enables the gesture navigation in the application menu and starts piloting the drone using his right hand. When pressing the Enable Video button, the drone's camera video feed is displayed in the application. At this clip, we can see the view inside the application, and at the same time, the user executing the gesture navigation commands and the drone responding to these commands. In the navigation feedback panel, the perceived navigation commands are displayed in the first row. In the second row, we can see other useful information, such as drone distance, heading, and altitude. When executing a yaw command, as the drone rotates, the position of the video feed panel is rotating accordingly, as it is designed to be placed in front of the camera. Now the user activates the camera control, and by using his left hand, he rotates the camera gimbal. He guides the camera to face up and down. By pressing the camera mode button, the video mode changes to infrared. Pressing again, the video changes to hybrid view. And pressing one more time, it returns to default RGB mode. By enabling the FPV mode toggle, the video panel is placed on top of the user's field of view. By pressing the menu position toggle, the feedback panel is now depicted in a stable position in front of the user. Finally, by pressing Reset Camera, the camera returns to its default position. Now the user demonstrates the drone takeoff and landing gesture. By rotating his palm upwards and raising his hand's position, the drone takes off. By lowering his hand position, the drone lands.
Now the presentation is finished for the augmented reality tools developed into the FASTER project. Thank you for your attention.
Hello, let me introduce myself. I am Panagiotis Karkazis from Synelixi Solution Greece, and I will present to you the communication technologies which have been developed in the context of the 5G Faster in order to facilitate the needs of the first responders in the disaster sites. Faster paid special attention to the communication tools because the networking infrastructure and its performance plays a crucial role in any disaster type caused either by natural phenomena or technological accidents or even human actions. Communication between the first responders and the command centers are not guaranteed in any case. So often it suffers by broken links, overloaded networks, or in many cases there is no any infrastructure in the site. So Faster offers communication resilient solutions to accommodate the most of the field conditions. For all these reasons, in Faster, we have a whole work package dedicated to resilience communication technologies and tools. And in this slide, you can see all the involved partners that we have worked together during the project in order to develop new innovative solutions and provide these solutions to the first responders and evaluate them during to the demos that we have run until now. So, the main objectives of Faster, according to communication capabilities, is to provide high-quality, resilient, and secure communication services, even under adverse conditions when existing communication solutions may be either unreliable or not available at all. So, Faster focus on the following. First, on usage of flexible 5G-enabled communication platforms for services related to the first responder use cases, on monitoring the quality of service and the network performance of the network, extending the range of the existing communication capabilities using UXVs, deploying independent emergency communication solutions, and providing a distributed trusted network using blockchain technology. In Faster, we investigated the design and the integration of the 5G-enabled communication technologies, considering the requirements coming from the use cases to facilitate the first responders. This kind of infrastructure protects responders in dangerous environments and enhances their capabilities in terms of situational awareness and communication. Let's consider a use case of a big earthquake affecting a populated area. The first responders in the field wearing personal protective equipment. That kind of equipment can be smart textiles for tracking biometric information and smart wearables for measuring and tracking environmental conditions. The 5G enabled infrastructure offers communication with low latency for near instant transfer of the sensorial data and high bandwidth for sharing large amounts of data from the faster tools like the 3D mapping service or the augmented reality services. First, we proposed an experimental implementation based on a 5G radio access network combined with a 5G packet core. This design is based on open air interface with a USRP base station, and this first version was validated in OTE labs. In the second version of this approach, a new power amplifier was designed and added to the system in order to extend the network coverage to 1 kilometer, and all this it was used in the Athens pilot last October. In this slide, you can see the architecture of the experimental solution and some photos from the equipment that was used in the pilot site. Next, OTE deployed a standalone 5G network in its R&D premises in Athens for the test and validation of the faster tools. The 5G testbed, consisting of 5G RAN and packet core, it has been used to run several tests focusing on low latency applications and network slicing. The network slicing provides a private connectivity to first responders while ensuring the quality of the offered services. A dedicated slice will be provided to them, so by this way we'll be able to fulfill the tool's requirements that the first responders use, and at the same time other users will not be able to use this dedicated slice, ensuring that the increased traffic demand which is seen when the natural disasters occur will not have impact on the connectivity of the first responders. To provide the required level of quality of service, we designed and deployed a monitoring framework based on well-known open-source solutions. The proposed architecture offers quality of service control of the running services through the monitoring and analyzing specific and relevant metrics such as latency, bandwidth, computational efficiency, CPU, and memory usage. The quality of service performance framework implements a closed loop consisting of monitoring, analysis, planning, and execution processes, which is called MAPE. The framework collects monitoring data from physical servers and networks, but also from virtualized resources like VMs, virtual machines, containers, SDN controllers, and so on. The important outcome of this process is the timely reaction of the services with respect to scaling and placement actions in order to optimize the performance and satisfy the user requirements during runtime. In this way, VNF forwarding graphs can adapt to the expected network performance and ensure the required quality of service of the running applications. Furthermore, the system uses machine learning algorithms to achieve optimized service performance and resource allocation. On the right side of the slide, you can see the architecture of the framework and how the services are communicating through the Kafka message broker. As you can see, the monitoring information is collected from different types of sources like OpenStack, Docker Engine, Kubernetes clusters, running instances of network services and VNFs, and then all this data are processed by the analysis service using pre-trained machine learning models, and the necessary actions are passed from the planning and execution service to the management and registration framework, which is responsible for the lifecycle management of the running instances of network services. Regarding the MAP implementation, as you can see, we have chosen tools which are open source and cloud native solutions. First of all, regarding the management and orchestration framework, we choose the open source Mano, which is one of the more mature proposals right now in the field of NFV. And as an NFVI, we pick the OpenStack, so any network service can be deployed as a set of virtual machines. Next, the analysis server is facilitated in an Apache Spark cluster in which we have deployed all the trained machine learning models for the analysis of the incoming data. And for the monitoring server, we based on the Prometheus monitoring server, and all these services are communicated with each other through a message broker. And at this point, this broker is the Kafka message broker, which is one of the most reliable and scalable solutions right now in this for this kind of application. As we mentioned before, one of the main problems that first responders face in the disaster sites is the limited network coverage caused to damaged infrastructures or to obstacles that block the signal. To address this kind of issues, Faster offers a network solution based on UXV's relay networks. By this way, we extend the existing communication network by utilizing groups of drones or ground vehicles to relay the communications from the nearest gateway point. The deployed network implements a mesh algorithm that ensures the adaptation of the UXV location in order to maintain the communication link at the required quality of service independently of the first responder location within the disaster area. As we realized from the pilot trials, the relay network based on drones can be deployed easily and quickly over the disaster site, providing network connectivity to the first responders to the exact point they are working on. Regarding the UXV equipment, we have two types of devices. The first one is the payload relay module, and the second one is the gateway module. The gateway module is the bridge, let's say, between the existing network, communication network, and the UXV relay network. And the devices, the payload relay devices, are the blue ones in the left side of the slide, and you can see these devices mounted on drones and ground vehicles from our last pilot activities. Another communication solution that FASTER offers is based on the Rescue device, which has been developed within the project. Rescue is a low-cost emergency communication device suitable to be deployed in the early stages of an emergency, allowing communication between first responders and civilians. The device is independent of existing communication infrastructure and allows encrypted transmission of messages containing basic instruction within the coverage of the device. To extend the communication range, several devices can be used in order to create an ad hoc broadcasting infrastructure. Several applications for mobile phones and smartphones have been developed, which enables the presentation of the critical information to the devices to different users groups like civilians and responders. So if we want to highlight the main capabilities of the rescue, first of all, we need to say that this system provides the ability to propagate short and encrypted messages to a target group of users in the disaster area. Second, we can cover big areas and extend the coverage by using multiple nodes and create a mesh network. And of course, this makes the solution very scalable, and it is independent of any existing networking infrastructure, which is very critical, especially at the first hours of the event. At the right side of the slide, you can see some screenshots. Some of them is from the user interface of the rescue. The second one is the alerting notification that we can see in our mobile phone when we are in coverage of the device, and on the bottom you can see the actual rescue device, which is very easy and simple to operate it. There is only one power switch. It is recharging through a USB port, and of course we have another button and an indicator that give us the operational status of the device. Last but not least, FASTER offers a distributed trust network through a blockchain and smart contract technologies, able to provide transparency across several parties and help align emergency demands for relief. This system is useful for bringing assistance and resources where and when it is most needed. This distributed trust network gives to the involved partners in the relief effort the ability to write and read relevant data on the open platforms to improve first responder reaction and, of course, their efficiency. The provided network operates as an ad hoc supply chain network, which provides First, a trusted, decentralized transparency across all parties, aligns emergency demands for relief with the available resources and the capabilities that provide by the first responders, connect all the mobile apps and application centers, IoT devices and drones and others in a distributed network of trust, and of course implements GDPR policies about the data privacy. In this slide, we're presenting a screenshot from the graphical user interface of the distributed trusted network, and also the data flow that the user should follow in order to register a new device with its attributes and the scripts that are needed in order to communicate with the specific device. The integration with the faster devices and services that are running at edge or fog level can be easily done either by using specific libraries that are provided or by connecting directly to the Kafka message broker in the fog level. Following this approach, we have made successful tests during the last pilots, integrating IoT devices like the Morse from University of Athens and services like POP from engineering and two-dimension mapping and analysis service from SURF. At this point, I want to thank you all for your time, and I hope that you found our proposals and our work interesting, and I hope that we also have the opportunity to work together in the future. Thank you again.
Okay, everybody, thank you very much for your participation today. Just a reminder that tomorrow we will have the workshops, which I think is probably the highlight, or at least one of the highlights of our symposium. So I highly encourage you to attend, even if you are not one of the panelists. This will be simultaneously translated from English to Japanese and Japanese to English, depending on the speaker. We'll have 2 translators at the time, working on 2 different channels with Zoom. So I highly encourage everybody to attend. Please do, if you can, and invite your friends as well to attend. I think we will gain a lot of this live session from both the Japanese panelists and also the European panelists. I think it's important that we have as many people there as possible, and I highly encourage you. Thank you, everybody, for your help in putting this together, especially all of the speakers that participated today. We will be broadcasting both of today's sessions in Japanese as well on tomorrow and on Wednesday. So this session that we just finished will be on Wednesday, and the earlier one will be tomorrow morning here in Japan. I mean, tomorrow early afternoon here in Japan. So after that, we'll be doing the panels, 2 consecutive panels, the practitioners panel and the technology panel. So thank you very much for your participation, and I hope you have a great rest of the day. For us, it's almost tomorrow in 15 minutes. So I'll see you soon, I guess. Thank you very much. Goodbye.
Thank you very much. See you tomorrow.
Tomorrow. Well, see you.
Bye.
Yeah.
Good night.